Okay, we are continuing with three-phase transformer connections, and we're going to take a look at the first objective from this module, which looks at the first three-phase transformer connection, a YY connection. And this YY connection comes basically from three single-phase transformers that are connected to form a Y primary and a Y secondary. The H winding from each single-phase transformer is connected to form the primary Y connection, and the X winding from each single-phase transformer is connected together to form the Y secondary. The rest of what they talk about on this page is just a bit of information out of the module. One of the important things to remember is almost all three-phase transformer connections will have a primary neutral, and one disadvantage of this YY connection with a primary neutral is third harmonics, and it's just really extra currents that can end up building on the neutral and heating the neutral more. Also, we want to remember the rules of Y systems are applied to both the primary and secondary sides of this connection. Now, again, this is maybe an easier way to look at how the three single-phase transformers are connected together to give us a Y primary and Y secondary system. If I look at three single-phase transformers, think of this as transformer A, this is transformer B, this is transformer C. They're all single-phase transformers, one H winding and one X winding. To make a primary Y system, we simply connect a line from our supply to the H1 of each single-phase transformer. So line A is connected to H1 of the A transformer, line B is connected to H1 of the B transformer, line C is connected to H1 of the C transformer. So a line is connected to the beginning of each winding of these transformers. The end of each winding of these transformers is connected together to give us a neutral point, and that neutral point is connected to our supply neutral. So whatever the supply system is that feeds the primary of this connection, the lines are connected on one end of the three windings, and the other end of the three windings are connected together to form our Y point and make a Y connection on the primary. And the very same thing is done on the secondary with the three X windings on the secondary to give us a Y connected secondary as well. Here's another way to look at that connection. And this is a little easier to see that it's the Y connection on the primary and the secondary. The H winding from A transformer is the first leg of that Y primary. The H winding of the B transformer is the second leg. The H winding of the C transformer is the third leg to make that Y connection. On the secondaries, the X winding of the A transformer is one leg of the connection. The X winding of the B transformer is the second leg. The X winding of the C transformer is the third leg. So it gives us both a Y primary and a Y secondary using the three single-phase transformers. Now we're going to take a look at this connection with a primary system voltage connected. The primary line voltage is 4160 volts. That is connected to our three H windings. And then we are going to get an output voltage from our three X windings. We have a ratio from primary to secondary of 6.933 to 1. And it's important to remember that that transformation takes place in the phase, from phase primary to phase secondary. And we can take a look at some values for this connection. What's the total kVA rating of the transformer bank? If we are using three single-phase 300 kVA transformers, then the total kVA rating of the three of them connected together would be 900 kVA. The rated primary phase voltage, if our system has a line voltage of 4160, we simply use the rule for Y voltages. We would divide 4160 by root 3 to get the rated phase voltage on the primary, which is 2400 volts. The primary phase current would come from the VA rating of each phase, which is 300 kVA, divided by the phase voltage, which is 2400 volts. 300 kVA divided by 2400 volts gives us 125 amps. And the rated primary line current, again, it's just the rule for Y, and the rule is phase current equals line current. So if the primary phase current is 125 amps, that is going to be the line current as well. We do the same thing on the secondary. Now, what is the rated secondary phase voltage? In order to find our secondary voltages, we have to work from the primary. If the primary line voltage is 4160 volts and the primary phase voltage is 2400 volts, we know that this ratio takes place from phase primary to phase secondary. So if we take 2400 volts and divide it by 6.93, we are going to get the phase voltage on the secondary. 2400 divided by 6.933 is 346 volts. We could almost call it 347. So our phase voltage on the secondary is 347. If that's the phase voltage, we know the rule for Y is line voltage equals phase voltage times root 3. And that would give us a line voltage on the secondary of 600 volts. What's the secondary rated phase current? To find that phase current, we would take the phase voltage, which is 347, and the VA rating for each phase. Primary VA equals secondary VA, so if the phase VA on the primary is 300 kVA, the phase VA on each phase of the secondary is 300 kVA as well. If I take 300 kVA and divide it by 347 volts, our rated secondary phase current would be 866 amps. Once we have the phase current, we know that in a Y system, the line current and the phase current are the same value, so the line current would also be 866 amps. So this will show you how to find voltages and currents when we have a set rating for our transformers. All right, the last example that we're going to look at is what happens with a three-phase transformer connection when we connect a set load on the secondary. This transformer connection is rated for 900 kVA. 300 kVA single-phase transformers connected together will give us a total rated load capacity of 900 kVA. In this example, we are going to connect a 750 kVA balanced load on the secondary of this system. Our voltage values will stay the same on the primary and secondary because they are rated. We always are using rated voltages, but the currents are now going to change when we use this load. If I'm going to look at what the primary phase and line currents are going to be, there are two ways we can find this. The first way is to understand that whatever load we have connected on the secondary is reflected back on the primary. And if we have 750 kVA on the secondary, it's the same as having 750 kVA on the primary. And if that's the case, then each phase winding would carry 1/3 of that load, or 250 kVA. If we know the phase volt amps and we know the phase voltage, we can find the phase current now. 250 kVA divided by 2400 volts will give us 104 amps. That is the phase current. I line equals I phase, so the line current's 104 amps. That is one way to solve the currents on the primary. A second, easier way to do this is, again, just to remember that the load is reflected back on the primary, and 750 kVA on the secondary is the same as 750 kVA on the primary. And then from there, just remember that the basic power formula we use is three-phase VA total equals V line times I line times root 3. If we want to find the line current on the primary, we simply rearrange this formula, and the total VA on the primary divided by the line voltage times root 3 will give us the line current. So 750 kVA divided by 4160 times root 3 will give us 104 amps. This is the line current on the primary, and I line equals I phase, so the phase current on the primary is 104 amps as well. It is a little easier to use this formula and just use line values. And you'll see that this gets a little easier the more we do it. To find the secondary phase and line currents, we solve it the same two ways. The load on the secondary is 750 kVA, and because it's balanced, we know each phase winding on the secondary carries 1/3 of that load, or 250 kVA. Now the phase current will be that phase VA divided by the phase voltage. So 250 kVA divided by 347 volts is 721 amps as our phase current on the secondary. And the rule for current is line current equals phase current, so the line current is also 721 amps. The easier way to solve this, again, is just to remember that the main power formula we use is the VA formula. Three-phase VA total is V line times I line times √3. To find the line current, we simply rearrange this formula, and line current would equal the total VA divided by line voltage times √3. So 750 kVA divided by 600 volts times √3 gives us 721 amps, which is the line current for the secondary. And phase current equals line current, so the phase current is also 721 amps. So hopefully this will help you solve for currents and voltages on three-phase transformer connections when you know what the load is connected on the secondary. From here, we go to delta delta.